Continue.
Everybody, this is our presentation on robust 4D radar inertial odometry. I am Marcus Badger, Region Who.
Sriram.
And first, this is what we're going to talk about today. We're going to start with an introduction and a motivation, then a methodology with some background, and then the results of our work. So if you see here, this is an example of radar slam. So if we were to play the video, what you would see is a car eventually moving and it's creating the map, and you get to see odometry. On the right there, you see the radar that's coming through, and you also see the camera that's coming through. So why would you even want to do something like radar slam or use radar instead of like LIDAR or camera? It's because during bad weather conditions, like you see here, like snowfall, rain, or night, LIDAR and camera tends to not perform as well as they are originally intended to. So this is our methodology for our odometry estimation pipeline. First, we start with a 4D radar that gives us X, Y, Z positions and Doppler velocity. And we also input IMU data. First, we start with the pre-processing, which determines outlier points and inlier points. And then from there, we get eagle velocity and filtered point cloud data that goes to our scan matching algorithm. From our scan matching algorithm, we get radar odometry and radar incremental odometry that then goes in our IMU pre-integration. And this allows our IMU data and our radar data to be fused to produce radar and IMU odometry. So first, we're going to start talking about the pre-processing part.
In the pre-processing part, the methodology consists of three main steps: initial filtering based on Doppler information clustering and estimating the probability of the movement of each clusters. We use linearly squared approach to calculate the eagle velocity based on Doppler velocity of each data point to detect dynamic object. Despite applying Doppler for filtering, the performance was under expectations. So we propose an additional algorithm. Then the project employs HDB scan on unsupervised clustering algorithm. The HDB scan is used because it can handle clusters with different densities. This algorithm helps in both the object separation and noise filtering because objects in radar data are located as clusters, but the noise doesn't. By assuming most of the environment is static, the project utilized the GICP algorithm to calculate the translation between new data and the buffer to estimate the overall translation. Then with the clustering results, the translation of each cluster is estimated with GICP, and the 3D Gaussian model is applied to estimate the likelihood that the translation of the cluster matches the overall translation. Dynamic clusters are identified and removed based on their probability densities.
So now we're going to talk about the methodology for scan matching. So in our scan matching, we basically do an extension from general ICP. We do something called adaptive probability distribution, GICP, where essentially this algorithm is used very well with radar, which is able to do scan-to-scan matching on noisy, sparse data, which you get from 4D radar data from point clouds. Next, we're going to talk about the IMU pre-integration.
So now I will explain how we integrate data from a 9-axis IMU sensor, vector nav 100, with radar odometry estimates using incremental smoothing and mapping and IMU pre-integration. This strategy significantly enhances the accuracy and the performance of localization in our system. And our methodology involves IMU pre-integration to aggregate angular velocities and linear acceleration data between keyframes. We integrate IMU measurements over time to compute relative motion and orientation changes, which effectively reduces the number of variables and computations needed during the graph optimization process. And further, I will explain the structure of our factor graph and how we perform graph optimization. We construct a factor graph where nodes represent states such as the vehicle's pose, velocity, and the IMU bias at different keyframes, at consecutive keyframes. And factors connect these nodes and represent various types of measurements and constraints, including IMU pre-integration factor, which compress multiple IMU readings into a single factor, linking consecutive poses or nodes based on the integrated IMU data. and an IMU bias factor, which assumes that the IMU bias remains constant between consecutive nodes, simplifying IMU bias integration and maintenance. And also radar odometry factors from the scan-to-scan matching odometry estimation process via fast APD-GICP, essential for refining the position and velocity estimates. And we also perform marginalization to manage the computational complexity by reducing the number of variables in the factor graph. So every 100 keyframes, we marginalize out the oldest variable and condense the past information into a new prior. This process ensures that the graph remains manageable over time. And overall, we use incremental smoothing and mapping to incrementally update the graph as new data becomes available, and linearizing around the most recent estimate to refine the trajectory and bias estimates effectively.
So now we're going to show a quick demo of our pipeline actually running. As you see here, we have the car going, and we get to see the nice point cloud going and the odometry working. So this is our actual video from our actual pipeline.
Then we conduct the experiment to evaluate the performance of our algorithm using relative odometry error. To compare performance, we test 4 different algorithms: the 40 radar algorithm from NTU, only point cloud filtering, only radar IMU fusion, and our overall approach onto datasets car park and nine-link from NTU datasets. The result in car park dataset shows that all our approaches performs better than the original NTU method. The overall approach has the best performance. Therefore, our approach provides a more robust and accurate radar-based odometry. The results in nine-link datasets also shows that the clustering algorithm and the initial IMU fusion method improves the performance separately, but overall algorithm performs below our expectations, although it's still better than the original one. The reason why this is happening requires more investigation.
Okay, so for our future work, we first want to enhance the dynamic point tracking algorithm while assuming that most of the scan is static. Next, we want to implement a back-end post-graph optimization to use other sensor modalities, such as GPS. Then we want to complete with scan intensity-based loop closure and deliver a complete scan system. As you see here, we're mostly only seeing radar odometry. Later, we want to make this into a whole SLAM system. Last, we want to perform experiments under harsh weather conditions to validate the robustness of our approach. The reason we didn't see that here is because old past radar data sets have these adverse weather conditions, but they're mostly for 2D and 3D radar. But for 4D radar, none of the data sets currently available publicly have harsh weather conditions being shown. Lastly, to conclude on what we've seen today, we basically presented a 4D radar with ion fusion with outlier rejection via HDB scan clustering. Overall, our methodology seeing the best results in the car park data set, and there was lesser performance in the NTU data set. And the 2 hypotheses we have for this is it may be due to filtering, removing too much of the point clouds and harder scenes that you will see in the NTU data set. And the last one is maybe the radar odometry fusion makes scan-to-scan matching more sensitive when we try to do this. But overall, our methodology outperforms the baseline 40 radar odometry from a 2023 paper that we are basing this off of for radar using 40 radar. Thank you.
Thank you.
We used